change in momentum always requires a net force. Previously, we've seen that the net force is equal to the mass of an object times its acceleration. This is Newton's second law. But if we think about that acceleration, an acceleration is a change in velocity with time. And if we distribute the mass, since a change in velocity is the final minus the initial velocity, then this is the same as a change in mv with time, which is equivalent to a change in the momentum with time. So this becomes an alternative way of writing Newton's second law, that the sum of the forces on an object is equal to its change in momentum in some amount of time. If the net force is 0, then momentum is conserved. Let's take a look at this example. We have a ball of mass 1 kilogram drop from a height 2 meters above the floor. It then rebounds to a height of 1.5 meters. We want to find the momentum immediately before the ball touches the ground and immediately after it rebounds. And then we'll use that to find the average force exerted by the floor on the ball. And we want to assume that the interaction happens in 1/100th of a second. So let's take a look at solving the first part of this problem. We have this ball and it falls from a height of 2 meters and rebounds to a height of 1.5 meters. And we want to find the momentum right before it touches the ground and right after it stops touching the ground. So that means we need to break the motion up into two different parts, the part before it hits the ground and the part after it leaves the ground. So let's think about before hitting the ground. So before hitting the ground, the ball drops from a height that's 2 meters above the floor. So it starts out 2 meters above and then it comes down, and we want to consider right before it touches the ground. So the part of the motion where the ball is in free fall. So if we just consider this part of the motion, we know that, well, we can write down some knowns because we are dealing with a free fall situation. We know that initially the ball is at rest. It starts from rest, it's let go, and it falls. We know that the change in the y position is going to be minus 2 meters because it falls 2 meters in the negative y direction, in the downward direction. And the thing that we want to find, our unknown, is what is the final velocity of the ball? Because if we know the final velocity, we can then find that momentum right before the ball touches the ground. So if I look at my free fall equations, I think I'll use the one that says that the delta y is equal to v naught squared minus v squared over 2g. And I want to be able to solve that for that final velocity. So first we'll multiply both sides by 2g so that it cancels here and we have a 2g delta y on this side. And then I will add the v squared to both sides and then subtract 2g delta y from both sides so that I get the v squared by itself. So v squared is going to be equal to v naught squared minus 2g delta y. And then I just need to take the square root of both sides. So that means my speed right before I hit the ground is going to be equal to the square root of the initial velocity squared, but that initial velocity was 0, minus 2 times 9.8, since g is always positive 9.8 meters per second squared. And then my delta y is negative 2 meters. And so the minus here cancels with the minus here. And I get a speed of 6.26 meters per second. And the direction would be downwards. So that's in the downwards direction. So immediately before the ball hits the ground, it's traveling at 6.26 meters per second in the downward direction. So the momentum of the ball right before it hits the ground is going to be equal to the ball's mass times its velocity. And the ball's mass is 1 kilogram times the velocity of 6.26 meters per second. And so that means its momentum will be 6.26 kilograms times meters per second, also in the downward direction. Now, after hitting the ground, the ball rebounds. And so next we want to look at, after it hits the ground, we want to look at the rebound phase of the motion, where the ball is starting out at ground level and going upwards. So once again, immediately after the ball leaves the ground, we are in a free fall situation because the only force acting on the ball is gravity. So once again, we can write down our knowns for this part of the motion. We know that once the ball leaves the ground, it's going to be traveling with some velocity, but then when it gets up to its highest point, then that final velocity is going to be 0, because when it reaches the highest point, it will momentarily stop and then turn and fall back down. We know that it rebounds to a height of 1.5 meters, so our delta y is 1.5 meters. And that's what we know for that part of the problem. The unknown that we're trying to find is the initial velocity, that velocity that it has when it just barely stops touching the ground. So if I look at this expression up here, if I look at this v naught squared minus v squared is equal to 2g delta y, I can rearrange that to solve for v naught squared. So now my v naught squared is going to be equal to 2g delta y, and this time it's plus v squared. So then once again I take the square root of both sides, and my initial velocity is going to be equal to the square root of 2 times 9.8 meters per second squared times my new delta y is 1.5 meters, and then plus the final velocity, which is 0 squared. So that's going to give me a value of 5.42 meters per second, and this is in the upwards direction. It leaves the floor with an upwards velocity. And then the momentum is going to be equal to the mass times that velocity. So that's going to be equal to 1 kilogram times 5.42 meters per second, which will be 5.42 kilograms times meters per second in the upward direction. So we now have found the momentum immediately before, and immediately after hitting the ground. The second part of this problem asks us to find the average force exerted by the floor on the ball, and to assume that the interaction happens in 1/100th of a second. So according to the previous slide, we know that another way of writing Newton's second law is that the net force is equal to the change in momentum with time. And that means that the change in momentum, that's the final momentum, minus the initial momentum divided by time. And in this case, the final momentum is 5.42 kilograms meters per second. That's the momentum after the ball touches the floor, and it's in the upward direction. It's a positive in the y direction momentum. And the initial momentum minus, well, the initial momentum was downward, so that's going to be a negative 6.26 kilograms meters per second. And then we divide all of that by the amount of time that the interaction took place, the amount of time that the ball was in contact with the floor, which is 1/100th of a second, or 0.01 seconds. So I'll write it here. The net force then is going to be equal to 1,168 newtons. So that's the result that we get from that calculation, that we have a net force of 1,168 newtons, and that would be in the upward direction since it's positive. Okay, are we done? Well, not quite, because what the problem asks us to find is not the net force, but the force exerted by the floor on the ball. So to go further, we're going to have to draw a free body diagram. So if we are looking at the ball, when it's in contact with the floor, we know that the weight of the ball is pulling downward, and then the floor is exerting a force on the ball, which is the normal force. So if we look at the net force, which is the sum of the forces that are acting in the y direction, we have a number for that, but we know that that's also going to be equal to the normal force minus mg, and we found previously that this has a numerical value of 1,168 newtons. So what we really want is the normal force, because that's the force of the floor on the ball. So if we solve for the normal force will be 1,168 newtons plus the mass of the ball times the acceleration of gravity. So plugging in some numbers, the mass of the ball is 1 kilogram, and the g is 9.8 meters per second squared. So that will give us a total normal force of 1,178 newtons, and that is the force of the floor on the ball, and the answer to part B. The next concept we need to look at is called impulse. And impulse is just a name for the change in momentum. So the impulse is equal to the final momentum minus the initial momentum. And if we rearrange that Newton's second law equation that relates force, time, and change in momentum, we'll find that the change in momentum is also equal to the force times the time that is required for the change in momentum. So another way of writing impulse is that impulse is equal to force times change in time. So if you are in an accident or some sort of collision, it's the forces that cause injury. The forces on your body cause your body to be injured, break bones, and do other nasty things. So in an accident, what you want to do is reduce the forces that are acting on a person's body. You want to make the forces small. Now the momentum, you're going forward in a car at a very fast speed, and then you're coming to a stop, so you have to have a certain change in momentum. You want to make f small, so the way to do that is to make the time in which the collision occurs bigger. And so you want to increase delta t. And the way that you can increase the amount of time for a collision is to collide with something that squishes. So this is why we have airbags in cars. The airbags increase the amount of time in which your momentum is brought to zero, and then that reduces the forces acting on your body. So here's a question for you. You know that a moderate force will break an egg. However, an egg dropped on the road usually breaks, while one dropped on the grass usually doesn't break. Why is this?